Welcome back to Electromagnetics Basics. In our previous episodes, we discovered what electromagnetic waves are. You encounter wave behavior every day, even if you don't realize it. As a wave travels through the world, every encounter tells a different story. Imagine throwing a ball against a wall. The ball bounces back toward you. Electromagnetic waves can behave in a very similar way. When a wave encounters a surface that it cannot easily pass through, part or all of the wave changes direction and travels back into the original medium. This phenomenon is called reflection. Reflection is one of the most common wave behaviors and plays a vital role in mirrors, radar systems, satellite communication, and many other technologies. Reflection follows a surprisingly simple rule. The angle at which the wave arrives at the surface is called the angle of incidence. The angle at which it leaves is called the angle of reflection. These two angles are always equal when measured from the normal line, an imaginary line perpendicular to the surface. This simple law explains why mirrors produce predictable images, and why engineers can accurately control reflected electromagnetic waves. Not every surface reflects waves in the same way. A smooth surface, such as a mirror, reflects waves in one predictable direction. This is called specular reflection. A rough surface behaves differently. Tiny bumps and irregularities cause the reflected waves to scatter in many directions. This is known as diffuse reflection. Diffuse reflection allows us to see most everyday objects because light is scattered toward our eyes. Reflection is everywhere around us. We see ourselves in mirrors because light reflects from the smooth surface. Satellite dishes collect weak radio signals by reflecting them toward a receiver. Radar systems transmit electromagnetic waves and detect objects by analyzing the reflected signals. Reflection is one of the most important tools engineers use to sense and communicate with the world. Now let's test your understanding. If a wave approaches a perfectly smooth mirror from this direction, which path will it follow after reflection? Think carefully before answering. Remember the law of reflection. The angle of incidence is always equal to the angle of reflection. Let's summarize what we've learned. Reflection occurs when a wave encounters a boundary and changes direction. Smooth surfaces produce regular reflections, while rough surfaces scatter waves in many directions. The angle of incidence always equals the angle of reflection. Reflection allows us to build mirrors, radar systems, satellite communication links, and countless other technologies. Next, we'll explore another fascinating wave behavior. Not every wave bounces back. Sometimes a wave enters a new material instead. As it crosses the boundary, its speed changes. Because different parts of the wave change speed at slightly different times, the wave changes direction. This phenomenon is called refraction. When an electromagnetic wave reaches the boundary between two materials, it may appear that the boundary itself bends the wave. But that's not actually what's happening. The real reason is that different materials slow electromagnetic waves by different amounts. As the wave crosses the boundary, its speed changes. One side of the wavefront enters the new material and slows down slightly before the other side, causing the entire wavefront to rotate. This rotation changes the direction of travel, creating the bending effect we call refraction. Although the wave's speed changes in the new material, its frequency remains exactly the same because it is determined by the source that generated the wave. A familiar example of refraction is light passing from air into glass. Light travels faster in air, but as it enters the glass, it slows down because glass is optically denser. This reduction in speed causes the light wave to bend toward the normal at the boundary. The amount of bending depends on the properties of the two materials and is accurately described by Snell's law. This simple yet powerful principle forms the foundation of many optical technologies, allowing engineers to design lenses, cameras, microscopes, telescopes, and countless other instruments that control and focus light with remarkable precision. When light leaves the glass and re-enters the air, the process is simply reversed. Because light travels faster in air than in glass, the wave speeds up as it crosses the boundary. This increase in speed causes the wave to bend away from the normal. Whether a wave bends toward or away from the normal depends entirely on how its speed changes when moving between two materials. If it slows down, it bends toward the normal. If it speeds up, it bends away. This is why refraction works in both directions and allows light to be precisely controlled in optical systems. Refraction isn't just a scientific concept. It appears in everyday life all around us. You've probably noticed that a straw looks bent when it's placed in a glass of water. In reality, the straw hasn't changed shape at all. Instead, the light traveling from the water into the air is refracted before it reaches your eyes. The same principle explains why swimming pools often appear shallower than they really are. Refraction also allows lenses in cameras, microscopes, and eyeglasses to focus light with great precision. Even one of nature's most beautiful sights, a rainbow, is created when sunlight is refracted and dispersed by tiny water droplets in the atmosphere. Refraction is one of the fundamental principles behind modern optical engineering. Eyeglasses use carefully shaped lenses to redirect light, helping us see clearly. Camera lenses precisely focus light onto image sensors to produce sharp photographs and videos. Microscopes and telescopes also rely on refraction to reveal details that are either far too small or far too distant for the human eye to see. Perhaps the most remarkable application is optical fiber, where light is guided over vast distances to carry enormous amounts of data every second, forming the backbone of today's high-speed internet and global communications. Let's summarize what we've learned about refraction. Refraction occurs when a wave enters a different material and its speed changes. Because different materials slow waves by different amounts, the wave changes direction as it crosses the boundary. While its speed changes, its frequency remains exactly the same because it is determined by the source. This simple principle explains many familiar optical phenomena and forms the foundation of technologies such as eyeglasses, camera lenses, microscopes, telescopes, and fiber optic communication. Next, we'll explore another fascinating wave behavior, diffraction. Imagine hearing someone speaking from around a corner, even though you can't see them. How did the sound reach your ears? The answer is diffraction. Unlike a beam of light that usually travels in a straight line, many types of waves can bend around obstacles and spread out after passing through a narrow opening. This allows sound to reach places that aren't in a direct line of sight. Diffraction is a fundamental wave behavior and plays an important role in everything from everyday sound to radio communications and many other wave-based technologies. When a wave reaches the edge of an obstacle or passes through a narrow opening, it doesn't simply continue in a straight line. Instead, the wave spreads out into the space beyond the edge or opening. The amount of spreading depends on the relationship between the size of the opening and the wavelength. The smaller the opening compared with the wavelength, the stronger the diffraction effect becomes. This is why diffraction is easy to observe with sound and radio waves, which have relatively long wavelengths, but is much less noticeable with visible light, whose wavelength is extremely short. Not all openings produce the same amount of diffraction. If an opening is much larger than the wavelength, the wave passes through with very little spreading and continues almost straight ahead. But as the opening becomes similar in size to the wavelength, the wave spreads out much more dramatically after passing through. This means the amount of diffraction is not determined by the opening size alone. Instead, it depends on the relationship between the wavelength and the size of the opening. Understanding this relationship helps explain why different types of waves behave so differently when they encounter the same obstacle or opening. Diffraction is happening around us every day, even if we rarely notice it. You can hear someone speaking or music playing from around a corner, because sound waves bend around obstacles and spread through open doorways. The same behavior can be seen in water waves, which spread out after passing through a narrow harbor entrance. Radio waves also diffract around buildings and other obstacles, allowing communication signals to reach areas that are not in a direct line of sight. These everyday examples show how diffraction helps waves travel into places that would otherwise remain unreachable. Diffraction is more than just an interesting wave phenomenon. It is an important consideration in modern engineering. Communication engineers rely on diffraction to help radio waves bend around buildings, hills, and other obstacles, extending signal coverage beyond the direct line of sight. Understanding diffraction is also essential when designing antennas and optimizing wireless networks for more reliable performance. In optics, diffraction sets a fundamental limit on how much detailed telescopes, microscopes, and other imaging systems can resolve. By understanding and managing diffraction, engineers can design communication and optical technologies that are both more efficient and more capable. One important question remains. Why can we hear someone speaking around a corner, but we usually can't see them? The answer lies in wavelength. Sound waves and radio waves have much longer wavelengths than visible light, so they diffract much more easily around obstacles and through openings. Visible light, on the other hand, has an extremely short wavelength, so it travels almost entirely in straight lines under everyday conditions. This difference in wavelength explains why radio signals can often reach behind buildings, while light cannot, and why many familiar experiences in daily life are shaped by the way different waves interact with obstacles. Let's summarize what we've learned about diffraction. Diffraction is the ability of waves to spread out after passing through an opening or bending around an obstacle. The amount of spreading depends on both the wavelength and the size of the opening, with longer wavelengths producing stronger diffraction. This fundamental wave behavior explains many everyday experiences and plays a vital role in technologies such as radio communication and wireless networks. Understanding diffraction helps us predict how waves travel when obstacles are in their path. In the next episode, we'll explore another fascinating wave behavior, interference, and discover what happens when two waves meet. So far, we've seen how waves can reflect, refract, and diffract. But what happens when two waves meet? Unlike solid objects, waves don't simply bounce off each other. Instead, they pass right through one another while temporarily combining. During this brief interaction, the combined wave can become stronger or weaker, depending on how the two waves line up. This fascinating behavior is called interference, and it's one of the most fundamental properties of waves. Let's begin with the simplest case. When the crest of one wave meets the crest of another, they reinforce each other. The same thing happens when two troughs overlap. Instead of canceling out, their amplitudes add together, producing a wave that is temporarily much larger than either wave on its own. This phenomenon is known as constructive interference because the two waves work together to create a stronger result. Although the larger wave exists only while the waves overlap, it's a powerful demonstration of how wave energy can combine through interference. Now let's look at the opposite situation. Imagine the crest of one wave meeting the trough of another. One pushes upward while the other pushes downward. So their positive and negative amplitudes combine and partially cancel each other. As a result, the overall wave becomes smaller than one or even either wave alone. If the two waves have exactly the same amplitude but are perfectly out of phase, they can cancel each other completely, leaving a flat line for that instant. This phenomenon is called destructive interference because the overlapping waves reduce or even eliminate the combined amplitude. One common misunderstanding is that when two waves interfere, they merge into a completely new wave forever. But that's not what actually happens. The interference exists only while the two waves overlap. During that brief moment, their amplitudes combine, making the resulting wave appear larger or smaller. As soon as the waves pass through each other, the overlap ends. Each wave continues traveling in its original direction with its original shape and amplitude, as if the encounter never happened. The interaction is only temporary, and the total energy of the system is conserved throughout the process. Interference isn't just a concept from physics textbooks. It's happening all around us every day. Noise-canceling headphones use destructive interference to reduce unwanted sounds by producing sound waves that cancel incoming noise. The shimmering colors on soap bubbles and thin oil films are created by light waves interfering with one another, causing some colors to be reinforced while others are canceled. And if you've ever dropped two stones into a pond, you've already seen interference in action. As the ripples spread and overlap, they create ever-changing patterns of larger and smaller waves, beautifully demonstrating how waves interact wherever they meet. Interference isn't just an interesting wave phenomenon. It plays a vital role in modern technology. In wireless communication systems, engineers carefully manage interference to improve signal quality and network performance. Antenna arrays take advantage of interference by combining signals so they reinforce one another in the desired direction while reducing unwanted radiation elsewhere. Scientists also rely on interference in highly sensitive optical interferometers, where tiny differences in light waves can reveal incredibly precise measurements. The same principles are used in advanced medical imaging and sensing technologies, helping doctors and researchers see details that would otherwise remain invisible. From mobile networks to scientific laboratories and hospitals, interference is a powerful tool that enables many of the technologies we depend on every day. Let's summarize what we've learned. When two waves overlap, they combine through a process called interference. If their crests and troughs line up, constructive interference increases the amplitude, creating a larger wave. If a crest meets a trough, destructive interference decreases the amplitude and can even produce complete cancellation. But remember, this interaction is only temporary. Once the waves pass through each other, each one continues traveling in its original direction, unchanged. Together with reflection, refraction, and diffraction, interference completes the four fundamental behaviors of waves that form the foundation of wave physics. We've now explored the four fundamental behaviors of waves. Reflection occurs when a wave bounces back after striking a surface. Refraction happens when a wave changes direction because its speed changes as it enters a different material. Diffraction allows waves to bend around obstacles and spread through narrow openings. And interference occurs when two or more waves overlap, temporarily combining to produce a stronger or weaker wave. Together, these four behaviors explain how waves interact with the world around us. They form the foundation of many fields, from electromagnetic waves and optics to wireless communication, medical imaging, and countless other modern technologies. By understanding these core principles, you'll be better prepared to explore the fascinating world of wave physics and the engineering systems built upon it. Reflection, refraction, diffraction, and interference aren't unique to electromagnetic waves. These four fundamental behaviors appear in almost every type of wave, including sound waves, water waves, light, and radio waves. That's why the same principles keep showing up across science and engineering. Whether you're designing an optical lens, building a wireless communication system, developing radar technology, or optimizing the acoustics of a concert hall, engineers rely on these wave behaviors every day. By understanding how waves reflect, bend, spread, and combine, you'll have a solid foundation for exploring optics, telecommunications, acoustics, and many other fields. Master these four behaviors, and you'll be well prepared to understand much of the technology that shapes our modern world. The wave behaviors we've explored aren't just scientific concepts. They're the foundation of many technologies we use every day. Cameras and microscopes use refraction to focus light and reveal fine detail. Fiber optic communication guides light across thousands of kilometers, carrying vast amounts of information at incredible speeds. Wi-Fi and mobile networks rely on reflection, diffraction, and interference to deliver reliable wireless connections, even in complex environments. Radar and satellite systems also depend on these same wave principles to detect objects, navigate, and communicate across great distances. From the smartphone in your pocket to the global communication networks connecting our world, engineers apply these four wave behaviors every single day. Understanding them is the first step toward understanding the technology that powers our modern lives. Before we wrap up, let's quickly review the four fundamental behaviors of waves. First, reflection. A wave bounces back when it encounters a surface. Next, refraction. A wave changes direction because its speed changes as it enters a different material. Then comes diffraction, where waves spread around obstacles or pass through narrow openings. Finally, interference occurs when two or more waves overlap and combine, producing a new wave pattern. These four simple ideas explain how waves interact with the world around us. Together, they form the foundation for understanding sound, light, radio waves, and many of the technologies that shape our everyday lives. Understanding how waves behave is the first step toward understanding many of the technologies we use every day. We've now explored the four fundamental wave behaviors: reflection, refraction, diffraction, and interference. These same principles are used by engineers in optics, wireless communication, radar, medical imaging, and countless other applications. But this is only the beginning. In our next episode, we'll explore how electromagnetic waves are generated and controlled, and discover how these invisible waves become the foundation of antennas, wireless systems, and the modern communication technologies that keep our world connected. Thank you for watching. Subscribe for more engineering insights.